So Anna Kosek has worked on several feasibility studies that you see. And let us see more about it.
Thank you, Kai. I'm Anna. I'm a postdoc here, and I've worked on several feasibility studies during the project, which was also a fun part of the project, I have to say. Yes, so today I will present 4 feasibility studies. Kai already talked about it. In the break, I'll also say a little bit about SYSLAB, especially for people that don't know much about it. A little bit about our research in DR interfaces, and we'll talk about briefly about this feasibility studies. And we prepared documents from all the feasibility studies. And if you are more interested, you can come to us or just read the document. Yeah. So the first feasibility study is, oh no, too far. Sorry. Yes. First feasibility study is about co-simulation, and in this work we cooperated with Office, and there were several people involved from Office in order to make happen. And also Oliver worked with me on this, and it took us around 5 months, not full time with breaks, but from beginning to end, to prepare this setup. And I also stayed 2 weeks in Office to learn the tools that they're using. And what was the motivation is that the control algorithms are becoming more complex, and they are no longer just one controller centralized that gets all the inputs and sends all the outputs to the system. It's we are also investigating transactional control, which would involve negotiation between actors, and is dependent on the messages. Then the outcome of the algorithm will be different, and also distributed algorithms that require a different way of simulating them in software. And also we know that the just electrical models is not sufficient to represent smart grid system. So therefore we wanted to develop a research tool that will help researchers to test the algorithms, to implement them in more realistic setup. Yes. And that's why we decided to use co-simulation. And I will explain a little bit, perhaps you don't know what is co-simulation. Is just a joint run of several simulations in a single computer or in several computers. But the idea is that the different simulators perhaps have different models, and they would exchange information between them at runtime. And in order to do that, to perform this kind of setup, you need the several simulations that you want to work with, and you need a tool that will coordinate all your simulations. So we have to track progress of the simulation time, because the simulators could run on different time steps. We have to synchronize the data exchange. When there is a data ready from one simulator to another, have to exchange it. We have to facilitate this data exchange, so the actual data has to be passed from one simulator to another, and probably has to be translated from one data type to another. And also, in the end, you have to coordinate the schedule of all the simulation. You have to start them and stop them, let one run, for example, in parallel with another one, and stop a third one, for example. So all of these things need to be taken care of if you would like to run 3 pieces of software to simulate a single system.
What do you mean by MD? The model is that a power?
Yes, for example, yeah, but could be anything else. Could be some mechanical model. Right. Could be anything. We'll go back to it later. I'll show. Yes. So in order to do that, you can facilitate these requirements in many ways. But how we decided to do it is to use a tool, a co-simulation orchestrator or a master that is in between those tools and coordinate them and facilitate this execution. So what we did is we use a simulation master from called Mosaic from Office. And this is now an open source tool that is available online right now. And what we wanted to do is, in this case, is to separate control strategy simulator from a power system simulator. So all the power system models, actually this is Ipsos' energy system simulator, so not only a power system but also energy, is simulated in this simulator, and the control, so all the algorithms would be here. And if the algorithm decides that some device has to be turned on or off or some action should be done, it should be passed to the simulator. That's the idea, yes. What we use here is we use multi-agent system because we believe it's very flexible in representing distributed systems, also with transactional control, because it's message-based system. So therefore, we can account to all of the messages being passed. Yes. And what we did in this feasibility study, this tool was developed. Ipsos existed in DTU for some time. We have developed this tool, MassSim. Office developed this tool, actually only improved because they had it already before we started. And we made this connection, configured Mosaic, and make interfaces to all the tools. Mm-hmm. So first of all, the problem with representing a control algorithm as a simulation in multi-agent system is that multi-agent system would just run continuously if there is something to run. If the agents want to do something, it would continue doing something. And it is real time, so therefore we had to find a way of stopping this multi-agent system with this control strategy. For example, stopping the negotiation halfway if we need it. And then starting again from the same point in order to have a discrete event simulator made out of this multi-agent system. So one part of it is actually the control architecture that is here a centralized agent, and it has several DR agents. And the second part of it is the platform is to start and stop the simulation and to continue it for a step depending on the orchestrator. And the other agent is just to grab the data and feed the DR agents with it, as if the data actually existed in the simulator, although it is in Ipsos. And this solution that we made is, how did we deal with time? Actually, we have ignored it. So there is no time allowed in here. So everything is event-based. So if there is a trigger from here, it triggers some actions. They work until they finish. And then once they finish, all the agents has to log. And then the simulation step is finished. So therefore, we assume that all the tasks finish within the simulation step. And it, depending on the simulation orchestrator, would say how long the simulation should run. Yes, so that was our solution. And the solution from Office was a little bit different. What they did with dealing with time, they decided to stop time, to freeze it. So therefore, they modified the software that was used for representing multi-agent system, Jade. So they modified this container. So therefore, all the agents would have to be dependent on time. So if the time stops, all the agents has to stop. So therefore, it's not allowed that any agents would be continuously working, checking something, or monitoring something. There has to be always time with these agents. So this solution is also not fully usable for us, because it's if everything depends on time, we don't have the full choice of the agents in the system. But that's just another solution that was made. Yes, and then we also modified Ipsus. And Ipsus is allowing to have controllers inside, and there could be a controller deployed in Ipsus. But it could only run once in every step. So if you have a controller code, it will be executed only once in the simulator, once there's a step. That's why we wanted to take the control out so we can execute the code several times if it's needed. So therefore, we also had to make this discrete event simulator out of Ipsus, because before Ipsus was not stopping. It was starting at some point and then stopping when the simulation was over. So we also had to implement this slave part of Ipsus to start it and ask it to run for one step, and also a way of getting data from Ipsus. And that was the setup with MassSim. So this is what we have made, the simulator. That's the co-simulation master from Office. And we had to make some translation between interfaces in order to fit an interface that was made in Mosaic. It's the reason why it's so complicated because actually it should be only arrows here, is that we did not have the interface of Mosaic beforehand, because at that time the software was still not open source, and so we were working on a collaboration agreement to get the software, but of course it takes time and bureaucracy to do this, so we were just blindly implementing these interfaces. That's why there is this connection. And the same with Ipsus. We had to do a proxy. And that was the setup for JadeSim, developed by Office. And what they had is they had a several interface for control. So they had a little bit different setup. OK, what we have learned from this, it took some time and some effort. And now we know that integrating software tools takes time and effort, although all of the tools were in Java. So there should not be really problems, but there were quite a lot. And both of the solutions for the multi-agent system simulator are not perfect. And I think we think we have to leave it to the designer to choose which solution he'd rather do. That's why we decided to put this other solution time variant in MassSim as well, just to give a choice. Yes. Also, we had some problem with the software installation. It was a research tool, Mosaic, so therefore it was not so easy to install it. When I went to Office, they just gave me a laptop with all the software configured, so I was very happy, and I was working on it 2 weeks. And then I wanted to take it back here to work on it a little bit more, and installing took me 1 week on the phone with a guy from Office. Now type this. It was very difficult. And also, at the beginning, the software was not open. Now it's open, so we had to have a collaboration agreement. And now, out of this fun experience, we got 2 papers. And first time, I just presented last week in Poland, and it was about the integration of the co-simulation tools. I had really a lot of nice questions, so that was very interesting. And the next one is we developed an algorithm that we tested in this co-simulation setup to see how good is an algorithm in the same setup. But what you had to do is here we look at the fuel consumption of diesel generators. And we had to make another integration to get the data out from Ipsus. But that was all. Yes. And now I'll talk about use case feasibility studies that took place at SYSLAB. So maybe not all of you know what is SYSLAB, so maybe I'll explain it quickly. It's a laboratory for intelligent distributed power systems. And we are at Riso, in a very nice location. And what we have is a lot of this power system components distributed in space and connected with cables. And we can play around with them and do some experiments, and I'll talk about some of them. OK, the second feasibility study. Yes, so what was the what was the reason for this feasibility study. We had a student that visited from TU Vienna, and he wanted to test his algorithm in our lab. He already tested the same algorithm in AIT lab, but since they have quite small configuration possible, and also they use simulators and we use real equipment, he wanted also to try it in our lab. So, so what we wanted to do is to test how fast you could actually deploy an algorithm in SYSLAB. And what we did, we had prepared for this experiment in advance because the student was supposed to come here for 2 weeks only. So what he developed was a multi-agent system, also in Jade, that contained his algorithm. And he had to connect, so in SYSLAB with every facility we have a computing node and an interface to it. So the student had to develop the interface between the agent with RMI to the SYSLAB node. So we have prepared this advance, and this interface was ready when he arrived. And what he did is he estimated the parameters of lines in SYSLAB. So he, yeah, perhaps I have to explain. So this is the map of SYSLAB simplified, and different colors are different locations. And all of these facilities are power system components, and these are cables. And now the red dots and lines is a setup in the lab. But the student didn't really need any setup. What he wanted to look is only the lines. So we gave him a setup from another experiment. And he looked at this line, also at this line until this point, and at cable C2. So what was the outcome of the deployment of the algorithm was really fast. It took us 1 day tops because he had to change some configuration in his multi-agent system, so it was really fast. But the problem is that he discovered that there was some wrong measurements in the lab because his task was to estimate the parameters of the line. He discovered that there is some switch of the sign, and he was very surprised. What, is my algorithm wrong? But then we discovered it was just a problem in configuration. So now we have corrected, and we have correct measurements. And also we had a technical failure. One of the cables tripped, and we could not use it anymore, so we had to change the configuration. So we had to start the experiments again. Yes? Yeah?
How do you take them later?
You can, yeah?
Yeah, what specifically was the wrong measurement? It was
Oh, yes.
just a meter that was giving
No, the meters were fine. Is because if the cable is going to substation, it has to have a plus, I think, and if it's going out, it has to have a minus here. So it was just the minus and plus were
okay.
different.
So the sign of the power
Yes.
was,
Yes.
okay.
Yeah, but we didn't notice. Usually when I do experiments, I just read from one point. I never read from substation, so I have never noticed this. But we have an error. Excuse me.
Yes.
Next one. Yes, then the two next feasibility studies will be about interfaces in SYSLAB, so I'll talk about a little bit more. It's basically is how to connect a component from a lab to a power system in general, to some other components or maybe other controllers. And here on this picture, it looks easy that these boxes fit easily, but in reality, it will be several interfaces. So we could implement a standard that is upcoming, but we never know if it will be accepted in the future, or it's perhaps difficult to use it. So then we perhaps develop another interface that is experimental and use it for a while. We have also some interfaces that are standard in the lab, but are not standard outside of our lab. So it would usually be that the DR would have several interfaces in parallel. So I'll talk about one of those interfaces that we have developed. And it was done together with Alex again. So Alex came back for the next 2 weeks in SYSLAB, and he was also developing these interfaces. And because it took quite a long time, it was taken over by another student in the lab. And what we wanted to do is simply add another interface in the lab, and we wanted to use a standard from automation. And with this automation standard, we wanted to facilitate communication and information models. So what is OPC UA? Okay, object linking and embedding for processes control unified architecture. Yes, well, it's a standard for communication and information representation in automation domain. It was also applied in power systems, but in some small areas. So we wanted to check if it's reasonable to use it or not. And there are some advantages from OPC UA embedded inside. For example, that is not constrained with a programming language. So it could be a client and server, could be different software in programming. Where, for example, right now in SYSLAB, we have to use Java or run through Java. There is a lot of advantages. One that is interesting, that it has a built-in security, which is quite a big topic now in power systems. That was also one of the reasons we tried to use it. Yes. And what we did is that we implemented an interface to a dump load. So this is the machine in SYSLAB. It has a SYSLAB node. And we were connecting to a PC with the new interface and test if it's actually running properly. So what we had is we implemented OPC UA server here and a client on the computer. And we still kept the RMI interface in order to check if we get the right data from the interface and if we actually can activate dump load or not.
So this SYSLAB node, that's a computer? Or what?
Yes, it's an embedded Linux machine that has the custom software that was made here. And it's a distributed SCADA system. So every facility has a computer like this that is configured to be representative for this machine only in the system. And all of them are connected between each other with optic fiber cable.
So there you simply had to map from this OPC UA to Modbus or something?
Yes, but in fact, it is already done in here. So there's a layered architecture in the SYSLAB node, and all the drivers are really on bottom. And there is some translation done into a data that is common in SYSLAB, and then on top of it, we implemented OPC UA. Yes?
Yeah, in this setup, why use the component dump load, not the other component?
I don't know. I think it was Alex that started on this one, and it's no harm in using it. It's easy to use. You can start it, stop it, give it some power output. You cannot maybe break it so easily. But there is no reason. Yes, and the setup in SYSLAB was very simple, so all we had to look at is one component, so we didn't care about the rest. And what have we learned from this? We have used the commercial software for partial implementation of OPC UA servers. So the client is provided by the library, and all we had to do is implement the data models and the connection between client and server. And since the time of the researcher that was doing this was limited, we had to put another person in order to finish the implementation. And because he had never heard about OPC UA, he had to learn about it first, so it took some time. He had to understand also the code of the previous person, and since the previous person left in a hurry because he had only 2 weeks, there was no documentation and no explanation how he designed. So therefore, it was redesigned, but we kept quite a big chunk of the code that we got from Alex. It's good that it was software engineer taking over the software, so that was an advantage thanks to Bo. Yes. Yes, and then we proved that the implementation is possible and it's feasible to use it. And now we want to look at it deeper, especially on the information model and OPC way. Last feasibility study. This one was, okay, just me and Oliver. And what we wanted to do is, again, look at the interfaces for DERs, but this time we wanted to look at service-oriented architecture, and we wanted to implement interface that will only execute services. So we wanted to see if it's possible, how would we design this interface, how would we represent information, would it even work? So that's why we did this study. So what we did is we took an experiment that was here. The algorithm was developed by Shui, that is a PhD student here. And we have helped implementing the algorithm in the lab. And maybe I'll explain quickly. So we have a voltage control, and there is a supervisory controller that look at the entire network to estimate where the voltage will be needed. And the local controllers sit on substations and control the unit DERs. So what we wanted to do is reuse data models that are exchanged between the entities. And we wanted to model only this part of the experiment. Yes, and what we wanted to do is to make these connections automatically, to improve these connections. So what we did, it was quite complicated. So we took only this part. We have modeled it in the service-oriented architecture model of software. So therefore, we had to model what are the connections between all the actors. So local controller was one of the actors, and it has to connect to unit controller. So we had to model this connection in terms of interfaces, data exchange, in terms of a protocol that these two units will use, and then use this to implement the actual interface that would be used on this point and also on this point. Yes, setup in SYSLAB was not so large. We had only an agent here on the substation. We have software on dump load and solar panels. Yes, so at the end, when I look at it from now, it took a very long time to actually model all the things in the system. It is quite complicated, but it takes the same time to actually implement it. If you are a software engineer, it really takes time. You have to design what is the data exchange, who's gonna write first, are you ask for data or you wait for data? You have to design everything. So since the model says exactly the same, it's like designing software, designing these models. And the experiment itself didn't take much time, is because we represented the system in the model that we could use directly to write the software. So it was very, very fast. And in fact, the model that we used could also be translated automatically to software. So therefore, the step from model to software will be non-existing, or maybe very small, maybe a few days of software engineering work. Therefore, the implementation could be tested very fast. And since we were working with interfaces, we could use the simulation of SYSLAB node. We didn't need actually real node for a while to test the interface itself. And out of this, we got also a paper in a conference in October, model driven the development of smart grid services using service architecture modeling language. Yes. Very interesting paper, read it. Yes, and that's all. Thank you very much. I really enjoyed working on the project, especially with all the fun things in the lab.